A signal can convey information about the behavior and attributes of all the phenomena in our universe, visible and invisible. In its most abstract form, a signal conveys information as a function of time or space. Digital signals, in particular, are fundamental to the world that we live in today. Digital signal processing is what enables us to model sound, in particular, in the way that we do, which is where we'll be focusing our discussion today. Such processing, this digital processing of sound, is achieved algorithmically through what is mathematically known as a Fourier Transform. At its most fundamental level, the Fourier Transform expresses any time-based signal as a distribution of its constituent frequencies. Sounds complicated, so to share a funny way to maybe intuit this that I found online, provided with a blended smoothie, the Fourier Transform finds its recipe. The Fourier Transform, shown in green, separates the ingredients, shown in red, in a way that lets us analyze what gives the smoothie, shown in blue, its unique characteristics, its flavor, its color, its consistency. To leave that smoothie metaphor behind and to bring the discussion back to the analysis of sound, the Fourier Transform converts a sound waveform, graphed as amplitude versus time, into a frequency spectrum, graphed as amplitude versus frequency over a specified time interval. As we can see here, this time-based function f, shown in red, can be re-expressed and actually sort of separated and broken down into a spectrum of these frequencies that comprise it, shown in blue. The Fourier Transform only re-expresses a time-based function. It doesn't change it in any way. Let's look at some examples. Here we see the waveform for a piano playing an A natural, a frequency of 440 Hz. Most of us are familiar with this visual representation of sound, where amplitude is graphed on the y-axis against time on the x-axis. But using Audio Explorer, a program that I found that functions simultaneously as an oscilloscope and more importantly as a spectroscope, we can see the Fourier transformation conducted in real time for a real-world application. On the left is our oscilloscope, displaying the amplitude versus time waveform. On the right is our spectroscope, displaying the amplitude versus frequency spectrum. While both graphs are interpretations of the exact same input, the spectroscope gives us information that's far easier to intuit. The spectroscope shows us that the vast majority of the sound produced by the piano comes from a single frequency. As this graph shows, 440 Hz produces the vast majority of the sound, as expected. It seems redundant to say that, but a comparison with different instruments playing the exact same notes of the same frequency puts that statement in context. Let's compare the respective frequency spectrums of a piano and a violin playing the same A major scale. From the first note of the violin, we see stark differences in the distribution of sound across the spectrum. The sound of the piano moving up the scale is largely contained to a single ascending frequency. We can see from all the activity in the higher registers that the violin has a quantifiably richer sound created by its many overtones. Now, for a similar, more controlled comparison, let's compare the frequency spectrums of a piano and a cello sounding at 440 Hz over 500 milliseconds. Just as was the case in the comparison of the violin, a single note on the cello resonates strongly through the seventh harmonic of that note, or significant term in the Fourier series, as it's called, while the piano only resonates through the first two or so. The effect of this is the same as it was for the violin, giving the cello a far richer sound, quantifiably richer sound, than the piano. In this context, the value of the Fourier transform is that it gives us a way to visualize what distinguishes different types of sound. It's the Fourier transform that converts standard waveforms into the informative, useful frequency spectrums that we examined today. Music composition programs like Sibelius use the data from these frequency spectrum graphs to simulate the sounds of real instruments. With the aid of the Fourier transform and through an analysis of the corollary frequency spectrums, the creators of Sibelius programmed string instruments like the violin and cello to have wider frequency domains than the piano, for example. Though such digital sounds can and never will truly reproduce the bona fide sound of an acoustic instrument, employing a Fourier transform to this input data that we've recorded today helps the creators of Sibelius to understand what distinguishes the color of a violin from